If you would recall, we've been studying convergence of series. We've been telling the story of sequences series and power series. And mainly we've been focusing on the story of convergence of series, how to look at a series and determine if it converges or diverges. We're trying to build up an intuition about whether a series converges or diverges, so we can tell just by looking at it if the series makes sense. Remember, what we're trying to do is plug values into a power series where the output is going to be a series, and we have to know if that output makes sense. Is it okay to plug that number into the power series and get that output? All right. So the big question here is does the series converge? Is the sum finite? Our first big piece of information was that if the series converges, then the limit of the terms must be equal to 0. But we also know that it's possible for the limit to be 0 and for the series to diverge. So it's not that the terms go to 0, it's how the terms go to 0. And the intuition that we developed around the integral test is we're wondering if the terms are going to 0 in some way faster than the harmonic series. The harmonic series is like the first thing that diverges, because when we integrate 1 over x, we end up with natural log of x, and then when x goes to infinity, the natural log goes to infinity. But if our exponent is slightly more than 1, then when we integrate, the x is still in the denominator, and so that term goes to 0, and our improper integral converges. So we're concerned with how the terms are getting to 0. Are they getting to 0 faster than the harmonic series? That's the way that one way that we can think about it. One way we can build an intuition about what's going on. So the comparison tests mean that we can focus a lot on the integral test and a p-series and the geometric series we looked at yesterday. Those give us some some series that are for which it's very easy to determine if they converge or diverge just by looking at them. And then the comparison tests allows us to look at a more complicated series or a series of more complicated looking terms and determine if it converges or diverges right away. So we want to look at another way we can get convergence, another way we can push terms to 0 faster than a harmonic series. I think this is 5. So another way that we can push terms towards 0 fast enough is by making the terms alternate. This makes half the terms negative. Sometimes if we make half the terms negative, that is, subtract half the terms, then we can get convergence. Sometimes we can do that. What that means is sometimes we take infinity and subtract infinity, and we get a finite amount. But sometimes we take infinity, subtract infinity, and end up with infinity. And sometimes we can take infinity, subtract infinity, and end up with negative infinity. Infinity is a very tricky concept. That's why we spend so much time studying infinity in calculus classes. So what we're going to be doing here in the alternating series test is essentially taking infinity minus infinity and seeing if it comes out positive. Or sorry, seeing if it comes out finite. That is a very sketchy way to describe things because I'm trying to build intuition and not necessarily proper mechanics. So don't be walking in front of Judge Judy and be like, oh, infinity minus infinity sometimes is finite. And sometimes it's infinite. And sometimes it's negative infinite. Let's write down the other thing that we're going to get out of the alternating series test, actually, before we do that. The other thing that we're going to get out of the alternating series test is that this is going to be our introduction to the two different types of convergence. There are two kinds of convergence. So our multiple choice test has gone from converges versus diverges to converges absolutely, converges conditionally, diverges. So we've gone from 2 choices to 3 choices. All right. So that's the other thing that we're going to be introducing with this alternating series test. Let's state the alternating series test. So first we need an alternating series. An alternating series is going to have this -1 to the n factor. Could also be a -1 to the n plus 1 or a -1 to the n minus 1. That could show up in different forms. But we need the an to be on its own always positive. Otherwise, if an is sometimes negative, then we're not going to get the alternating. The alternating comes from this -1 to the n part. So this -1 to the n could be a -1 to the n minus 1 or -1 to the n plus 1. It could be a -1 to the n minus 1 or a -1 to the n plus 1, depending on whether we want the first term to be positive or negative, and whether we start at n equals 1 or n equals 0, and the starting value of n. Note that the terms without the alternating part should always have the same sign. So the an over here is the term. These are the terms without the alternating part. So there's nothing fishy going on here. This is just us making sure that the series is actually alternating. So here's what saith the alternating series test. First, the series is alternating. Second, if the limit of the if the terms are decreasing, and two, the limit of the terms is 0, then we can conclude that series -1 to the n times an converges. If the terms decrease and the terms decrease to 0, then the alternating series converges. If the terms are alternating in sign, they decrease and decrease to 0. I'm going to change my numbering. So if the terms decrease, that's this first one. Oh, actually, first alternating. The second one is the terms decrease. This third one is the terms decrease to 0, or the limit of the terms is 0. Then we get to our conclusion. So 1, we have the alternating. 2, the terms are decreasing. 3, the terms are decreasing to 0. We can conclude 4, the series converges. The way we want to read this is that if we have terms that are going to 0 and they alternate, then we get convergence. Alternating is another way to get convergence. Alternating is a way to get terms to go to 0 fast enough. And the usual first example, this is the alternating harmonic series is conditionally converging. We know that the harmonic series on its own diverges, but the alternating harmonic series is converging. If I make half the terms negative, then we will get a finite sum. So here's our alternating harmonic series. 1 minus half plus a third minus a fourth plus a fifth minus a sixth. So first, we know that the series is alternating. Or actually, we should say that the terms are alternating. Alternating signs on the term. Number 2, in absolute value, the terms are getting smaller. If I make the denominator bigger, I make the fraction smaller. And the terms decrease and they decrease to 0. Since the terms are alternating, the terms decrease and the terms decrease to 0. The alternating harmonic series converges by the alternating series test. That's the important part right there. So here, this alternating harmonic series converges. The rest of it is just details that we have to bring forward. Alternating is another way to get convergence. Alternating makes the terms go to 0 fast enough. The conditional part of the convergence means that the only reason is because the only reason the alternating harmonic series converges is that it's alternating. The alternating harmonic series converges, but the harmonic series does not converge. So the reason that this is getting the conditional convergence tag is that the only reason the alternating harmonic series converges is the alternating part. The only way to get convergence is to make half the terms negative. So that's what conditional convergence is. The other kind of convergence is absolute convergence. If we can make all the terms positive and the series still converges, then we say that the series is absolutely convergent. In case you're wondering, this is what I was looking up on my phone because every semester I forget how to spell the word absolutely. I can't remember if there's an E in there. I know it ends in an E, but I can't remember if you just stick the E-L-Y on or if you have to drop the E. I don't know why I can never remember. 20 years teaching this class, I'm never going to learn how to spell the word absolutely. I'm going to have to look it up every single time. I think it's all those vodka ads that they used to run. If a series converges, but the terms in absolute value, if we make all the terms positive, the series diverges, then the series is conditionally convergent. And from the example that we just had, the alternating harmonic series the alternating harmonic series converges by the alternating series test, but the regular harmonic series diverges by, let's use the integral test or P series. So the alternating harmonic series is conditionally convergent. Absolute convergence is a stronger condition. Absolute convergence is better. If you can get absolute convergence, that's the one that you should go for. Absolute convergence is better. Absolute convergence is the stronger condition. What this means in practice is that we should only invoke the alternating series test if the only reason the series converges is that it alternates. So the way I usually phrase this is I say only bring up the alternating if you need to. Only bring up the alternating if you need to bring up the alternating. So for example, here's an alternating series, but it's an alternating 1 over n squared. So we're going to have a 1 minus a 4th plus a 9th minus a 16th plus a 25th and so on. The series is definitely alternating, but we're not going to bother invoking the alternating series test because the series is absolutely convergent. We're not going to mention the alternating because we don't need the alternating. We get convergence in absolute value. The series 1 over n squared converges all on its own. I don't need to make half the terms negative to get convergence here. The series 1 over n squared converges, so this series is absolutely convergent. If we need to justify the 1 over n squared converging, the series being 2 greater than 1, or we can use the integral test because this is something that we wouldn't mind integrating. It's not so bad. So if you've got absolute convergence, that's the one that you want to bring up. That's the stronger condition. That's better. This series, alternating 1 over the square root of n, the absolute value of the term diverges, or the series made up of the absolute value of the term diverges. So here we're going to use the alternating series test. Since the terms in absolute value diverge. So we look at this series, we see that the terms decrease to 0 and they alternate. So, but the terms do not, the series does not converge if we have the absolute value. So this is conditionally convergent. Since the terms alternate, the terms decrease, and the limit of the terms is 0, we can conclude that the series is convergent by the alternating series test. Since the series made up of the absolute value of the terms diverges, because it's a p series with p equal to 1/2, which is less than 1, the alternating series is conditionally convergent. Absolute convergence is the stronger condition. So that's the one that we should go for if we can get it. Remember that alternating something, or alternating and decreasing, is something that we add to, we already have to have the terms going to 0. If the terms aren't going to 0, then the series diverges. Doesn't matter if it's alternating, if the terms don't go to 0, the series diverges. That's one of our, that's what the one we always have to remember. Let's consider the sequence of partial sums for an alternating series. The first term is just going to be A0. Then the next term is going to be A0 minus A1. Then the next term will be A0 minus A1 plus A2. And then the next term will be A0 minus A1 plus A2 minus A3. And then it continues on from there. We can see that the alternating and the decreasing towards 0 will give us a convergent series just by looking at the sequence of partial sums. Let's graph the sequence of partial sums on the number line. Over here, we're going to have 0. Now, the first term in our sequence of partial sums is A0. The next term in the sequence of partial sums I should have named it, but I didn't. I'm going to give each of the terms in the sequence of partial sums names. Orange names. So this will be like S0, and then here's S1 and S2 and S3 and so on. So here is S0. Now I want to graph S1, the second term in the sequence of partial sums. That's going to be A0 minus A1. So we start up here at A0. And then the next term is A0 minus A1. Since the terms are decreasing, we're going to subtract, but we're not going to go past 0. Here's A0 minus A1. We know S1 will be there because we subtracted A1. A1 is less than A0, so we won't go past 0. That's the terms are decreasing part. Now the next term in the sequence of partial sums will be A0 minus A1 plus A2. So S2, here's our second term. Our next term, we're going to add because of the alternating, but we're not going to go past A0 because we're adding less than we just subtracted. We added less than we just subtracted, so we won't go past S0. The next term in the sequence of partial sums is A0 plus minus A1 plus A2 minus A3. So we're going to subtract, so we're going to go back the other way, but we're going to subtract less than we just added, so we won't go past S1. And then this goes back and forth forever, eventually zeroing in on the sum of the series. The sum will always just be in between any two consecutive terms in the sequence of partial sums. My favorite thing about the alternating series test is that it has a sound. You know those door stops that you screw into the door and it's like a little spring with a rubber end? That when you, yeah, that's exactly it. That's the sound of the alternating series test. It has to stop somewhere at the sum of the series. This is why we need the alternating, so we can add, then subtract, then add, then subtract. This is why we need the terms to decrease, so that we can add less than we just subtracted, then subtract less than we just added. And this is why the terms need to go to 0. Otherwise, the gap between those two consecutive terms will be whatever the limit of the sequence is, or limit of the terms is. So, this is how we visualize the alternating series. If someone asks you to to explain the alternating series test, all you got to do is go brrrr, and then that's it. You can do that anytime as a tutor. Working as a tutor, someone says, I don't really understand the alternating series test. Brrrr, and then just walk away. Maybe I'll make that video. I'll make it look like a normal video. So I'm going to set up and say alternating series test on the paper, and it'll be like 45 minutes long. But right at the beginning, it's all no word, no introduction. I just have it written down alternating series test, write down what the series is, and then just go, and then let the video run for like 45 minutes. And then put chapters in it, like something happens later on in the video. I don't believe this chapter. That's still nothing. That was going to be my plan, but I'm 5 days too late for that. So, oh well. So it's not that the terms go to zero, it's how the terms get to zero. One of the ways to get the terms to zero fast enough is to make the terms alternate. Now, we did mention that conditional convergence is weaker than absolute convergence, and I haven't explained why conditional convergence is weaker than absolute convergence. The short version, the TLDR, is that stuff starts to break down in the conditional convergence series. One of the things that we can count on with addition is that addition is commutative. A plus B is equal to B plus A. Can't prove that, it just is, and everybody understands that. In an absolutely convergent series, I can take the terms, infinitely many terms there are, we can add them up in whatever order we want. The order in which we add the terms does not affect the sum. Absolute convergence has nicely behaved addition. We like that. In a conditionally convergent series, if we rearrange the terms, we will get a different sum. That is not what we want from addition. In a conditionally convergent series, order matters, even though it's addition. If you add the terms up in the different order, you will get a different sum. There's a cool proof for this, but this particular lecture is too small to contain. So that's going to do it for today. That's going to do it for this week. I will see you all on Monday. Have a good weekend. And thanks for playing.